Okay, so let's talk some power series here. So this was the example that you had given me. So one of the maybe helpful ways to just wrap your head around what's taking place here is you could just write out a few of the first few terms. So this starts with n equals 1. So what that means is when n equals 1, that's going to be our first term. So we're going to have negative 1 squared times x minus 2 to the first divided by 1 times 2 to the first. And then because of this giant sigma notation, that means we're going to add on the next one. So we will have negative 1 to the third power times x minus 2 squared divided by 2 times 2 squared. Next term you would see would be negative 1 to the fourth times x minus 2 cubed divided by 3 times 2 cubed, and so on and so forth. So that's all this power series is saying, is this gigantic infinite sum where our n's are going from 1 to infinity, but our x's, we're allowed to plug in whatever we'd like. So for instance, if we plugged in x equals negative 7, we would just plug that into each of the terms and then evaluate that to get something. Okay, so the first thing we can talk about is the derivative. Okay, so let's talk about the derivative of this, because this is a function. When we take its derivative, what we could think about is taking the derivative of each of these individual terms. So if we take a look at the derivative of this, well, this term here and this term here, these are just constants. And then we have this x minus 2. And so we have this constant times x minus 2. Derivative of that is just going to be the constant times 1, and then the derivative of the constant will be 0. So all that's left here is negative 1 squared divided by 1 times 2 to the first. So that's going to be the derivative of the first term. The derivative of the next term, we're going to have to use the power rule. There we go. So we're going to have to bring down the exponent. So we have 2 times a negative 1 to the third times x minus 2. This is raised to the first power divided by 2 times 2 squared. Then take the derivative of the next term. Again, we're going to use the power rule. We're going to bring down the 3, and what we're left with here is a negative 1 to the fourth. We subtract 1 from the power. And so what we notice is that we're going to have a really nice pattern taking place. That when you take the derivative of each of these individual terms, the same rules are just going to apply. I'm going to bring down the exponent, and then I subtract 1 from the power, and everything else is the same. So instead of having to do this by each of the terms, we can do what's called term-by-term differentiation. So what that tells us is that when we have n equals 1 to infinity, I can just take the derivative of this whole thing with respect to x. And that's all the derivative will be. So n, again, we see it's just going to vary as different numbers over here, but really the derivative is taken with respect to x. So I bring down the exponent of n. So I will have an n times a negative 1 to the n plus 1 times x minus 2 to the n minus 1 divided by n times 2 to the n. And so that's the idea of taking the derivative, is you see that the rule is just each term has its derivative taken, so you're just going to do that to find the derivative. Same thing with the integral now, is if I want to now take the integral of each of these terms here, so if I take the integral of f of x dx, well, instead of now bringing down the power, we add 1 to the power and divide by the new power. So this would be negative 1 squared. I now have x minus 2 to the second power. I divide by that 2, and then I still have the same thing of 1 times 2 to the first. Next term over here, I add 1 to the power, so I have negative 1 cubed times x minus 2 cubed divided by 3 times 2 squared. And then so on and so forth. You see this one would be negative 1 to the fourth times x minus 2 to the fourth divided by 4 times 3 times 2 cubed. And so on and so forth. So again, the same rule is going to apply here, that when I take the integral of it, I'm just going to take the integral of this original thing. So I have negative 1. So we still have the sum here, n equals 1 to the infinity, I have negative 1 raised to the n plus 1 times x minus 2 raised to the n plus 1 divided by n plus 1 times n times 2 to the n. And so that would be my integral. However, because anytime we take the integral of a function here, it's the definite integral, we need to have a plus c. So don't forget about that plus c. So there we go. So those are the easy computational calculus things you can do. Now, talking about the interval of convergence now leads us to a much more interesting discussion about power series. Okay, so if we look at this original function, our original function f of x over here, we want to ask what values of x can I plug into this and still have a finite number? Okay, so if we started a much simpler series, so let's say, for instance, we start with a, I don't know, let's do an x to the n, and n is going to go from 1 to infinity. We see what this power series is we're going to have an x to the first plus x squared plus x cubed plus all these other things. So we'd like to understand, okay, what values of x can I plug into this so that way this whole sum isn't going to shoot off to infinity? For instance, if I was to say x is equal to 2, then I'm going to get 2 plus 4 plus 8, a whole bunch of things. This is going to go to infinity. That's not good. However, if I was to have something like, let's say, 1/2 to the first plus 1/2 squared plus 1/2 cubed and so on and so forth, this will, oops, sorry, this should be 1/2 to the third. This will actually converge for us. Why? Because this here would just be a geometric series. So we have a geometric series, so this is going to converge. Now, there's an obvious number that we could plug in for x that would make this converge very clearly, right? If I was to plug in x is equal to 0, what I would get as my sum is 0 plus 0 plus 0 plus 0 plus 0. So this obvious term right here is always going to make this converge. So if we look at this function here, we could say, okay, what value of x could I plug in where this obviously converges? Well, we see that when x is equal to 2, what we're going to get is we're going to get f of 2 is equal to the sum n equals 1 to infinity of negative 1 to the n plus 1 times a 0 divided by n times 2 to the n. So this whole thing just ends up being a whole bunch of zeros, which is obviously a convergent thing. It just adds up to 0 in this case. As a note, some of these might be like just a 1 or a 2 or something and not just always equal to 0. But we see that this choice of x, very simple, very nice. But we'd like to know how far out can we go? How much wiggle room is there? Like for instance here, x equals 0, that was good. 1/2 was good, but 2 was no good. So this interval of convergence is all of the x values that we could plug in and get a finite number when we take this infinite sum. So how we're going to accomplish this is you have here, you had this limit as n tends to infinity. You're going to take this absolute value of our a sub n plus 1 divided by a sub n. So now that since there's absolute values, the negative 1 part doesn't really need to be included. It's just going to make these things positive or negative. It doesn't matter. So what we'll have is we'll have the limit as n tends to infinity. Our a sub n plus 1 is going to be our x minus 2 raised to the n plus 1 divided by n plus 1 times 2 to the n plus 1. Now, when you divide it, you're just going to multiply by the reciprocal. So we have the reciprocal will be an n times 2 to the n divided by x minus 2 raised to the n. Now, when we start to simplify this, this is where we have to be careful. Okay, when we think about repeated things, so like if let's say we have 3 to the n plus 2 divided by a 3 to the 4n. When you have the same base here, you could then subtract the exponents. So this would be a 3 to the n plus 2 minus 4n. And so this would, if we simplify this, this would be 3 to the negative 3n plus 2. So if we have the same base, we can do this to subtract the exponents. So always, when we do these, this x minus 2 term is always going to simplify tremendously for us. Because this just says we have n copies of x minus 2, and here we have n plus 1 copies. We could cancel all but one of these. So up top, we're left with an x minus 2. Now, when we start to cancel other things, we have n copies of 2, and we have n plus 1 copies of 2. So this would be like 2 times 2 times 2 times 2, and this would be 2 times 2. You get the idea here. We're going to cancel all but one of these terms as well. So on the bottom, there's going to be still a copy of 2. Now, what we have left is we have this n, and then we have an n plus 1 on the bottom. Remember, if you have n divided by n plus 1, you cannot cancel these. This is going to be a big no-no, so we don't want to be canceling this. We have to leave this for right now. Now, we don't always have to, we're not going to just keep it there forever, but we'll see what happens now. So what we have at this point of the limit n tends to infinity of all of this is the limit is only going to affect the n terms. It's not going to affect this x minus 2. So I'm going to take this out, but because there's absolute values around it over here, we need to have absolute values around over here. Now I have the limit as n tends to infinity, and because n is always positive because n is going to infinity, I can drop the absolute values, and I have an n over 2n plus 2. So this now is just a limit that you would have seen in Calc 1. Divide by the highest power of n if you would like. So if you multiply this by 1 over n, multiply this guy by 1 over n, you're going to get an absolute value of x minus 2. The limit as n tends to infinity of 1 divided by 2 plus 2 over n. This thing goes to 0. So this whole thing is going to be just 1/2. So this limit is going to be 1/2 the absolute value of x minus 2. Now, at this point in the class, I believe you should have done the ratio test. So the ratio test, what that's saying is that this limit here for the ratio test, this is only going to work for us when this limit is going to be less than 1. Other words, if we're thinking about a fraction being less than 1, so if we have a sub n plus 1 divided by a sub n is less than 1, what that's saying is that a sub n plus 1 is going to be less than a sub n. So really we're saying the later terms are smaller than the first term, so that makes sense for us. So what we now set up is we set up this to figure out when is this less than 1. So we have 1/2 absolute value of x minus 2 is less than 1. And now we just solve this. So we'll have absolute value of x minus 2 is less than 2. And now when you have this type of inequality, this becomes the sandwich inequality. -2 is less than x minus 2, which is less than 2. Getting x by itself, we have this would be 0 is less than x, which is less than 4. So what that means is on the interval 0 to 4, we know that this function will be convergent. Now notice up here, we said x equals 2 was the really nice, obvious term. That is right smack dab in the middle here. That is exactly how all of these work, is that really nice term is there, and then everything else just goes out to the two sides. But if you also remember from the ratio test, not only do you have that this converges when it's less than 1, if you remember when this equals 1, we have no idea what happens. We don't know what happens at these endpoints, so we have to check those. So then the idea now becomes we need to check what happens when x is equal to 0, and we want to check what happens when x is equal to 4. So what that looks like is that we're going to take those values and we're going to plug them into our original power series up here. So we will take a look to see what happens to the power series n equals 1 to infinity of -1 to the n plus 1. And then when we have 0 plugged in there, we're going to get a -2 to the n minus 1. Oops, sorry, plugged in the wrong one. -2 to the n. -2 to the n divided by n times 2 to the n. Okay, great. So now we just do some manipulation to figure out how does this work. Well, if we start to simplify this, we're going to get a -1 to the n plus 1. Take out a -1 from this, we're going to have a -1 to the n times 2 to the n divided by n times 2 to the n. Then we can cancel off these 2 to the n's because they're really just going to be the same thing. And we could combine these if we would like to, and that this is now going to be the sum from n equals 1 to infinity. We have the same basis, we add the exponents, we're going to have a -1 to the 2n plus 1 divided by n. Now this series, we could ask, what does this look like? So we could start plugging in some values here. N equals 1. We see the exponent is going to be 3. So I'm going to have a -1 to the third divided by 1. And then I have plus the next term. If I plug in n equals 2, I have -1 to the fifth divided by 2 plus -1 to the seventh divided by 3, and so on and so forth. So really, if we notice, this is always going to be an odd number. So -1 to an odd power is always just going to be a -1. So this is now the sum from n equals 1 to infinity of -1 divided by n. Or in other words, this is -1, the sum from n equals 1 to infinity of 1 over n. Now, what's happened is that we no longer have a power series. We just have a regular series, and we have to figure out, does this thing converge or diverge? This should be very familiar because this is the harmonic series. This bad boy diverges. And then you do the same thing over here with x is equal to 4. You would plug that in. You're going to have a slightly different thing that happens now, and you want to figure out what happens. Does this function converge or not? So here what we notice is that it does not converge at x equals 0. At x equals 4, we figure that out. If it does converge there, then this would be your interval of convergence, 0 to 4, and we include 4. However, if it doesn't converge at this, then we just leave it like this, and it doesn't converge at the endpoint, and this is the radius of convergence. So that's a quick overview on power series. So hopefully that is helpful.